Okay, so my name is Sławomir Kubacki. I'm from Warsaw University of Technology. I have a privilege to chair the session number 1. So the first presentation will be by Nicolas Goffart from Cadence. So yeah, the floor is yours. Please start.
Thanks for the nice introduction, and thanks to all of you for coming today. I'm very happy to start the day after also the nice keynote we had. My name is Nicolas Goffart, indeed, and I'm working at Cadence Design Systems Belgium, or you might better know previously Numerica International. I'm also doing my PhD in La Sapienza with Professor Pirazzoli, and today I will show you how we can go from high-fidelity, high-order simulations to reduced-order modeling for unsteady shockwave boundary layer interactions. Let me give you first a bit of context and the idea of the methodology. We've always looked for improvements in aircraft and engines efficiency, and this is for sure something that is not going to end soon. We know that the global air traffic is going to grow, and we expect that the fleet will be doubled in 15, 20 years. And at the same time, we want to limit the impact of this fleet to come on the environment and the climate. And my work is particularly focused on turbomachinery aspects. And for this, we would like to reach transonic regimes efficiently. And transonic regimes in turbomachinery is a bit tricky. First of all, because we have our beloved shockwave boundary layer interactions, and we know that it affects negatively the aerodynamic efficiency. It can lead to flow separation, flow distortion, and we have also this low frequency unsteadiness. And well, we are dealing with turbomachines, so we have a succession of rotor and stators, and this provokes further periodic perturbations that comes and interact with the separated area and further affect the efficiency. And if we want to push the limits of efficiency further with confidence, we need design tools that are able to predict those phenomena accurately. And in turbomachinery for CFD, we have a wide variety of methods. We can go from a single blade passage to a full annulus. We can go from a single row to a single stage to multi-stage configurations. And we can also go from Reynolds average simulations where we model turbulence to high-fidelity simulations in which we resolve turbulence. And to properly capture SBLIs, we need high-fidelity simulations. However, they are still costly. And in the industry, we still rely mostly on runs and new runs in the design chain because of their short turnaround time, the robustness, and the relatively good accuracy. In between runs and new runs, you also have harmonic methods. The idea of harmonic methods is that we want to benefit from the inherent periodicity of turbomachinery flows so that we can obtain an unsteady solution, as in new runs, but on a single blade passage mesh, as in runs. However, in some methods, and also with SBLIs, the assumption we take to model harmonic turbulence can give some problems, and this is what we want to address in my work. So from the context, we know that we want to improve the treatment of harmonic turbulence in harmonic methods for SBLIs, but that only high-fidelity methods can get the physics correctly for SBLIs. So we will go from high-fidelity simulations using a high-order solver to study the forced transonic flow over a bump, and in particular the harmonic turbulence. And then we will go to reduced order modeling using that high-fidelity data that we have generated, and we want to find how to take into account this harmonic turbulence. And I will talk especially on the non-linear harmonic method, but I will introduce it later. So this is the content of my talk. I will first introduce you the high-order high-fidelity solver, and then I will go through the results of the forced transonic flow over a bump. And before concluding, I will show you first attempt to this reduced order modeling for the NLH. So the higher the solver, well, I'm very sorry for these slides. I hope you will agree with me later that it is the most boring one, but it's still important to mention all of these. So the numerical schemes for the solver are the flux reconstruction approach for the spatial discretization. You can think of it as discontinuous Galerkin. And here it will be fourth order accurate. For temporal discretization, we use a simple explicit Runge-Kutta scheme, fourth order accurate also. We will be performing implicit larger simulation, so there is no subgrid scale model. We have also an efficient shock catering strategy, combining the Ducrot sensor and an artificial viscosity method. We will also employ for additional robustness, positivity preserving limiter, and we also provide synthetic turbulence with a digital filtering technique at the inlet of the domain. Now that we know all of this, I will go directly to the test case. It's a transonic flow over a bump. The geometry comes from a PhD thesis in KTH in Sweden. And well, it's a Mach 0.7 flow, and there is a bump on the bottom wall of the wind tunnel. So for certain pressure conditions, you have this shock wave developing in the channel. And what is particularly interesting in that work for harmonic methods is that they studied the influence of a fluctuating static pressure to mimic the rotor-stator interactions. And also very interesting is that they the frequency is relatively high compared to what we can find in the literature, high enough to be relevant for turbomachinery applications in terms of reduced frequency. So the corresponding high-fidelity simulation setup is the following. So we will use the same bump geometry, of course, the same flow conditions, except that we reduce the Reynolds number by a factor of 20 to make the simulation affordable. And I will show you 4 cases. So there will be one that I call the baseline case, in which we have static pressure at the outlet of the domain that is fixed in time. And then 3 forced cases with a fluctuating static pressure at the outlet following a sine wave, and the amplitude will be always the same, 2% of the mean, but the frequency will be different, and we will go from 250 Hertz to 500 Hertz to 1000 Hertz. And you can see what it gives, what we can expect from a U-round simulation in the 500 Hertz case. And on the right, you can see the domain, the mesh, and the boundary conditions. It's nothing very fancy, but well, we have 80 million degrees of freedom, and the mesh resolution is typical for implicit larger simulation. It's not DNS-like, but it's not so far in the end. And I like to start always by some flow animations. So here is the numerical clearance at mid-span for all the forced cases. So you can see that we have our turbulent boundary layers on both walls, also at the top wall. The boundary layer is separating much earlier than the shock location. So we have this lambda shock pattern with this weak oblique compression wave. And the separated shear layer is unstable and breaks down to turbulence a bit more downstream. So we have this intense vortex shedding taking place and also persisting in the downstream boundary layer. And these are the force cases. So you can see, especially for the 1000 Hertz, regularly we have this upstream propagating wave that comes and interacts with the shock. And this is actually something that we want to study. It is a desired effect. To summarize how the flow is behaving, I would like to compare the weighted per multiply PSD maps of wall pressure. And here I will start with the baseline case. On the top, it's the PSD map for the top wall pressure. And on the bottom, it's the PSD map for the bottom wall pressure or the bump wall pressure. I will start with the bottom. So you can see we have around Struwell 1, we have this the incoming boundary layer. And then, as I said, we have this intense vortex shedding starting in the interaction and also persisting in the downstream boundary layer. And so for this, we have a Struwell number of around 0.1 after the interaction. And you can see also in a subset of the separated area, we have a very low frequency, 2 orders of magnitude lower than the incoming boundary layer. That is corresponding to the weak oblique compression wave. And that low frequency is also visible at the top wall. So we have the entire shock system that is moving naturally at this very low frequency. If now I force the flow at the lowest frequency, 250 Hertz, there is almost only the forcing frequency that is affecting, that is most affecting the variance of the signal. We have also this for the 500 Hertz case. And if we keep increasing at 1000 Hertz, we'll still see, of course, the influence of the forcing frequency, but we start also to recover the baseline behavior with the Struhal number that is 2 orders of magnitude lower than the incoming forcing frequency. So we go from a fully locked configuration when we have a very low forcing frequency to we start to see a decoupling between the baseline and the force flow when we increase forcing frequency. We are interested, as I said, in the harmonic content of the flow. And so for this, I will use phase averaging to extract it. I use 10 bins, so you can read this plot from top left, bottom left to top right, bottom right. Here it's for the streamwise velocity in the 500 Hertz case. And to summarize this plot where it's time history, so we can compute Fourier transform. And I can show you the amplitude and the phase of the first harmonic. And for me, the first harmonic is the forcing frequency. And you can see that for the streamwise velocity in the boundary layer, we have two structures. We have one starting from the separation point that is extending following the shear layer, and then the separated shear layer, and then that goes down on the bump wall further downstream. And then we have a second structures appearing even more downstream. I can do that for all the cases, of course. So here is for the 250 Hertz and the 1000 Hertz. At 250 Hertz, you can see we have the same structures as in the 500 Hertz one, starting from the separation point. But because we reduce the forcing frequency, we increase the wavelength of the perturbation, and therefore the structure is extending more downstream. And actually, the second structure at 500 Hertz case is lying outside of the figure for the 250 Hertz case. And at 1000 Hertz, well, the flow is not responding that much well to the forcing frequency, so it's a bit more difficult to see those structures, even though we have a regular pattern. And to come back to the very beginning of this talk, I'm interested in the harmonic turbulence. And so we can do this the same for, actually we can do the same for every quantity, of course, but here is the turbulence kinetic energy. Again, the first harmonic amplitude and phase at the forcing frequencies. And what I want to show you is that we have coherent structures that are similar for the 250 Hertz and 500 Hertz case, with once again a second structure appearing at 500 Hertz that is again lying outside of the figure at the 250. But beneath the shock system, we have the same structures all the time. And so that is to say, to have a zoom on the phase, we have an outer layer with a single and very strong structure that I called C1. And then we have an inner layer with 3 substructures of alternating sign that I call C2, C3, and C4. You can see also at 1000 Hertz, we don't have, well, we can see maybe C1, but the rest of the structures is not converge well. And again, it's because we do not have a lot of harmonic content at that frequency. And well, we are also, well, we are interested in this harmonic turbulence, and I could also derive the budgets of this harmonic turbulence. I'm not going to enter in the details of all the budgets because it's a lot of data. But what I want to show you is at 2 stations, so the station 1 that is going through C2, so the first structures of the inner layer, and the station 2 that is going through C3 and C1, I want to show you the harmonic production. Harmonic production, there are a lot of contributions. For U prime, there is in total 8, and for U prime, V prime, there is in total 16. But actually, only 2 out of them are necessary to recover the full production term. And these are contributions from the mean shear and its modulation. And here I'm showing this for the 2 stations. I'm showing this for the production of U prime, and U prime, V prime. And you can see indeed that the dashed blue line is exactly on top, almost, except for the station 1 at U prime, but is on top of the full production term. And I will use that fact later. And actually, I will use that for the reduced order modeling because it's the last part of my talk. First of all, this reduced order modeling is in the framework of the nonlinear harmonic method. So let me introduce it a bit further for you. It's a method initially developed by He and Ning in '98, and that has been implemented by my colleague Stéphane Villemain in Cadence Fine Turbo solver and improved since then. The idea of the method is that we decompose the flow variables into a mean component and into a sum of perturbations, because we have a lot of perturbations in turbomachinery flows. And then we assume that each perturbation is harmonic and can be decomposed into a sum of harmonics. And we put that decomposition into the U-rounds equation. We can derive a set of equations for the mean component and a set of equations for each harmonic of each perturbation, the real and the imaginary part. And all those sets of equations are coupled together, so we need to solve the equations simultaneously. But at the end of the day, when you have the solution for each component, you can reconstruct as a post-processing step an unsteady solution. But the power of the NLH resides in the fact that you solve the equation on a single blade passage mesh. This is very efficient for most of the cases, let's say, but not for our transonic flow over a bump. First of all, I want to show you that there is no difference in the mean flow between U-rounds and NLH, and this regardless of the Reynolds number, regardless of the perturbation frequency. And I could also show that with the implicit large simulation results, even though I didn't show it indeed today. And so for this, I'm showing here the mean contours, the contours of mean density. And I'm not going to take bets on which one is which, because there is still one chance of two. But it's very difficult to see which one is which, right? And actually, U-rounds is on the left and NLH is on the right. But if I look now at the harmonic content of the flow, it is different, and that is the problem, because we want to obtain the same results as U-rounds. Here I'm showing the first harmonic amplitude of pressure at the bump wall, and you can see indeed between the NLH in solid and the U-rounds in dashed, we have a clear mismatch. And this is attributed to the way we handle turbulence in the NLH method. To be more precise, to close the equations of the NLH method, we need two turbulence models. We need one for the mean equations and one for the harmonic equations. For example, if I use an eddy viscosity and I use the NLH decomposition, I will reach those expressions for the mean and the harmonic turbulence stresses, which means that we need, for example, a mean eddy viscosity and a harmonic eddy viscosity. And an assumption we take to close in a straightforward way the equations is that we freeze turbulence in time. So we say that the harmonics does not have any effect on the eddy viscosity. But doing so leads to problems for our force transonic flow over a bump. And so we wanted to answer that question, how to account for this harmonic eddy viscosity. And our idea is that it could be deduced from high-fidelity simulations. So as a first attempt, I will use what I showed you for the production. So I will derive here analytically a very first and simple model, starting from the fact that we are in a two-dimensional flow that is dominated by shear. So the production of turbulence kinetic energy is the product of the eddy viscosity and the square of the shear. If I use the decomposition of the NLH, I will come up with those three terms. And actually, the last two correspond to the harmonic production of K. From high-fidelity data, as I showed, the production of K is actually half the production of U prime, and corresponds to only two terms. That is these ones. And now I will take the assumptions that the left terms correspond to each other and the right term correspond to each other. And when I combine these informations, I can actually derive this expression for the harmonic eddy viscosity. So minus 2 times the mean eddy viscosity times the ratio between the modulation of the shear and its mean. And I want to show you the a priori performance using U-rounds data on the case at 500 Hertz. So on the top, it's the eddy viscosity, the harmonic eddy viscosity from U-rounds, and on the bottom, it's from the model. And I show two Reynolds number. The left one is, the lower one is the one from the high-fidelity data, the implicit large simulation I performed. And on the right is from the experiment. And you can see, first of all, that we are capturing, even though it is a very simple model, we are capturing not that badly, both quantitatively and qualitatively, the harmonic eddy viscosity. We have those three different structures appearing, and there's just the first one that is split in two because we follow the harmonic shear. Apparently, it is not supposed to be like that, but it's still a very good agreement for such a simple model. We have the same agreement for 250 Hertz, and at 1000 Hertz, again, it doesn't work. So with this, I will draw some conclusions and give you my perspectives. We wanted to go from high-fidelity high order. So we generated high-fidelity data using a high order solver on a forced transonic flow over a bump. And we could extract the harmonic component of the flow and study harmonic turbulence. If you're interested, and I hope you are, of course, there is a paper that has been accepted for publication in AIAA journal. So if you want, stay tuned. And then we went to reduced order modeling. We wanted to improve harmonic turbulence in the nonlinear harmonic method. And so for this, we showed encouraging results using a simple and analytically derived model for the harmonic eddy viscosity. As perspectives, we would like to bring this model to improve this model so that it becomes relevant for industrial applications. So first of all, the first step is to perform the a posteriori check of the model. So actually implementing it in the NLH and check that it gives better results. But then we will need to extend it for 1000 Hertz because we also have a problem at that frequency, but the model doesn't work. We could take into more effects. We could exploit machine learning algorithms to derive the model. And finally, we could also extend the database to more realistic case, actual turbomachinery flows, first a linear cascade to stay two-dimensional, let's say, and then 3D configurations to include even more effect in the database. So with this, I thank you for your attention. And if you have any question, of course, do not hesitate. Thank you.